Everyone here at Team Kestava, good morning, maybe good evening. All I know is you're hard at work studying for the PE exam coming up here shortly. Another review problem, just a little guy, but it's structural based. But I think it's going to be something that you could very well see on the morning portion of the civil PE exam. So you're all going to need to know it. Let's jump in there. See you in the classroom. A solid masonry column has a cross-section measuring 32 inches by 32 inches. The column is subjected to axial compression force of 110 kips. That's quite a lot, which includes the weight of the column. Okay, that's nice. With an eccentricity, we're not ton, of 5 inches, about one axis. What is most nearly the maximum axial compressive stress caused by this loading? The first thing that always catches me when I was studying is understanding when they call out stress. They call out stress a lot in the PE exam. And stress, when I was an undergrad, you're like, oh, stress. Yeah, as structural specific, you hear it all the time. You're like, yeah, stress, strain, oh, all that fancy stuff. But did you really understand what it was when you were learning it? Personally, to be honest, I didn't fully grasp it. I know that might sound silly, and you might be clicking out of here right now going, holy shit, I'm not listening to this guy. But let's just drive the point home. Stress is equal to a force over some area. The force can be any type of units you want. It could be pounds, it could be kips, it can be number of grandmas, it can be stones, it can be cats, I don't care. But it's some force, and then divided by the area. It could be inches, it can be feet, it can be miles, it can be kilometers, it could be whatever. Again, it could be whatever, but it's a force divided by an area. That is what stress is. So you need those two components in order to find a stress. So just drive that home. That's the best bit I can tell you, at least from my own personal experience, that helped me the most. And as you can see here in all of our solutions, it is a force over an area. So that is stress. So there you go. Well, we have a column here. We have masonry. Oh my gosh, this is terrifying. Well, this actually has nothing to do with masonry. They just threw it in there to give you a little bit more information to maybe throw you off. Because remember, in the PE exam, every problem, just about half of the info you can scrape away because it's not needed. And you need to know that because these problems are designed to give you an abundance of information and for you to understand not just how to use all the information to solve problems, but how to determine which information you need and which information you do not need to solve the problem. In this case, the material doesn't matter. They are simply asking for a stress. Stress is no different in wood, in masonry, in steel, in plastic, in silly putty. Stress is stress. All materials aside, it doesn't change that. Stress is universal, baby. Okay, so we have a column here. Well, how do we find stress in columns? Stress in columns is through the following equation. Actually, it's anything, beams, anything. Stress, we'll call it C, compressive stress, because that's what we're looking for, equals P over A plus or minus MC over I. Now, you can find this. I personally have the CERM, the Civil Engineering Reference Manual. I have, what is this, the 15th edition. So for me, the 15th edition, you can find this equation in 44-12. It actually gives an image similar to the one we have above, and it gives you those equations, and it gives you a quick little background as to how it was derived. So that's where I would go if you didn't remember it offhand, and I actually had it tabbed. I had it tabbed with this exact equation on the tab, so I just knew flip that sucker over right there. Well, we have some unknowns. What is P? P is just your force, so that's easy. P is 110 kips, and if we look at our units, kips and inches squared. So we know we can remain in kips, so that's fine. Area. What area? What are we talking? Are we talking this surface? We're talking this surface? Are we talking this surface? We're talking about the length of the column. What area do we want? We want, for stress, the cross-sectional area of your column, because if it was just a concentric force, just kind of think about it in the real if you were like a kid playing around, if you had a Lego here, and you're pushing down with your hand on that Lego, boom, boom, boom. Look at that, it's a Lego. You're pushing down on that Lego. For a stress, as we talked about, it's a force divided by an area. In order to find the stress inside of that Lego, it's just the total force divided by the area of that Lego that the force is acting normal towards. Normal is just perpendicular towards, so perpendicular coming down on your Lego surface. And that force gets distributed out across the entire square footage, or cross-sectional area to give you the stress acting on the Lego. Okay, so area is just going to be up above 32 inches by 32 inches. That's going to equal 1,024 square inches. Again, it's kips in square inches, so we know we can keep the units just like that. Next is M. M is moment. And you might be saying, well, what moment's going on here? Well, if we scroll up, we know there's an eccentricity of 5 inches, so this is not a concentric load. Concentric is the load is perfectly on the centroid of the column, which is right here. But in green here, we have a 5-inch eccentricity to where that point load is acting on our column. And if we think about it, again, we go back to, now let's go back to as a kid, if we had a really thin, pool noodle. Let's go with pool noodle, even though I got a square pool noodle and we all are round. When you had a force acting downward, and say it wasn't perfectly concentric, so your hand was slightly off that pool noodle, and you're pushing down on your pool noodle, what happens? Well, what happens, right, is that pool noodle is going to deform like that. So that thing is going to bow out to the side. And that creates, so you're bending. So what does that mean? We have internal bending stress in our column. And it's doing something, you could say you have internal bending moment in the column. Just like when we have a beam that's bending, we know that we have internal bending stresses. And you might be saying, well, when we have a beam, say we have a point load acting on the midpoint of the beam, that is what creates our moment. But in this case, we don't have that. We have a force acting along the length of the column. So where the heck is our moment? Our moment, as we know, is still equal to a force times a perpendicular distance. Well, the perpendicular distance is 5 inches, because that's the eccentricity from the force to the centroid of the column. And our force is 110 kips. So moment is going to be 110 kips times 5 inches, which equals 550 kip inch. So if I kind of draw that one more time, here's the centroid of our column. We have force acting right here. We have E as our eccentricity, and what that's generating is, if this is, I'm just going to call this axis XX. We have force eccentricity about that axis. That means we're going to get, in green, a moment that is rotating about that axis. And when that's happening, you're getting rotation, which means you're going to get deformation of the column very slightly, but just like that shape, which we talked about with the pool noodle above, okay? So that is where our moment is coming from. What else is next? We need C. C, we know, is the distance from the centroid of our column to the extreme fiber. Well, the extreme fiber, I'll scroll back down to this one, is, let's let's see, what do I want here? If we treated it, again, like a concrete beam, because this just always clicks better in my head, if it was bending like this, you would have cracking that would start to form on that face because, right, you have internal tensile stresses building up, and then you have equal and opposite compressive stresses building up on this face. So if I draw it in blue here, the extreme fiber for compression is along this blue face here. So that distance is going to be from your centroid to your extreme fiber. So that is C. Well, C is just, in that case, 1/2 of the depth of your column. And the depth and the width of your column are the same. They are both 32 inches. So C is going to be equal to D over 2, which equals 32 inches over 2, which equals 16 inches. Okay? And now we just need I. I is your moment of inertia. And for rectangles, I is equal to BD cubed over 12. That's just for rectangles. We know that this is B. We know that that face is D. So for a perfect square, we know that B equals D, which means we could rewrite the equation for moment of inertia for a square to be D cubed over 12. Okay? But again, that's just for a square. D to the fourth over 12. BD cubed over 12 is for rectangle. And that is for the rectangular shape of this internal cross-section of the column, okay? This, if you're like, how do you remember those off the top of your head? What if I can't remember off the top of my head because I'm remembering so much this PE exam? This equation, again, in the CERM, I actually have it tabbed as just an I. If you go to the appendices in the back, A-114 is the page number, and it's Appendix 42.A. You'll see centroids and area moments of inertia for basic shapes. So all of that information is laid out back there for you. Also, you have the AISC Steel Manual. I have the 14th edition, and we all know our beautiful tabs. If we whip it open, I have a tab called Section Properties, and that calls out on page 17-37, Table 17-27, and that gives you properties of geometric shapes as well. That gives you eyes, that gives you S. What is S? We'll get there in a second. Gives you areas. So those two locations is where you go to find this information so you don't have to remember it off the top of your head. Okay, let's find I. So I is equal to BD cubed over 12, which is 32 inches times 32 inches cubed over 12. And again, you can see here that you could just lump that additional 32 in and raise it to the fourth if you wanted. That proves right there how that equation transforms once you have two lengths that are equal to one another. That equals 87,381.3 inches to the fourth. That is going to give us everything we need to plug in. So to reiterate, stress is going to be equal to P over A plus or minus MC over I. Well, what the heck is with the plus or minus? The plus or minus comes into effect because, let's see, I'll draw it right here one more time. Just driving this concept home. We have our axis right here. We have our centroid. So we have internal stresses going on. We have compressive stress that is uniformly distributed. That is representative of P over A, force over area. So you have a total force divided by the total cross-sectional area. Easy, right? Then if I go green, we need to represent the moment that is introduced into our cross-sectional area. Well, that is not an even distribution. That actually comes across as that type of loading. And what you actually get is, depending on which way your eccentricity is being applied, right? So in our case, the eccentricity was on this side. So in this case, you're getting additional compressive stresses on the, we go blue, on this face of your column, extreme fiber, like we talked about. But then, I draw in yellow, on the other side, that back face, you have additional, or you're introducing tensile stresses on that side, because as we talked about right here, if it were to be concrete, if enough bending stress was introduced into the column, you'd actually have cracking on that far face because you have too much tensile stress building up on that extreme fiber. So that's what's happening here. So the plus and minus, when we're looking at compressive stress, so the blue face, that is when we want to add MC over I. But when we're looking at the yellow face for potential compressive or tensile stress, we don't know which one is controlling, you want to subtract MC over I, because the tensile stresses just take away, they counteract the compressive stresses, okay? And on the flip side, you're just adding more compressive stress on top of your compressive stress from your distributed load, okay? Hopefully that was okay. It's a little difficult to get across sometimes. Let me know in the comments. Let me know. You can just take a big dump all over me. It's fine. I'm used to it. You know, you're an engineer. What are you gonna do? Hopefully, I'm helping somebody out and it's clicking for somebody. That's the key here. So for our case, we no longer have a question mark. This is just going to be a plus. So compressive stress equals 110 kips divided by area, which is 1,024 inches squared, plus M, which is 550 kip inch. C is 16 inches, divided by I, which is the crazy one. What was it? 87,381.3 inches to the fourth. All of that is going to equal 0.2 kips per inch squared. Let's scroll back up the top. Let's go green. Oh, baby, I like the looks of that. Let's go with A. I think that's a completely reasonable solution. Don't go anywhere yet, because we're going to do this more quickly, very fast. A little trick for you. Here we go. Right back down. Well, how can we make this go more quickly? Well, another way to write stress, P over A plus or minus MC over I, this portion can actually be changed to M over S. And S, you're like, what the deuce? Well, C over I is actually equal to S, and the way you can prove that is like this. C equals, like we said, D over 2, and I is equal to B D cubed over 12. So if we plug all those in, M times D over 2 over B D cubed over 12 equal to M over S. But what is S? Well, S is equal to BD squared over 6 for rectangles. And again, that can also be found in the AISC Steel Manual in the Geometric Properties Table 17-23, I believe it was. Sorry, Table 17-27 in the back of your Steel Manual. And is that true? Well, let's see. So if that's the case, what does this reduce down to? If we reduce this down, we know that it's going to be m over so b stays, one of the d's gets canceled out, so squared, and then it's going to be 12 divided by 2, which is 6. So m over bd squared over 6, that is equal to s. So there you go. M over S is equal to MC over I. So if you want, instead of finding C and I independently, you can actually just solve for S and have one thing to look for, and that will also get you your answer. So there it is, Team Castiva. I hope this was informative to you. Like and subscribe. Tell somebody. Figure out what stress your life is under right now. Is it grandmas over kilometers, or is it, soft baby kittens, cute kittens over inches squared? Let's figure that one out. Leave a comment below. Let me know what you're feeling, what type of stress you're feeling, and I will see everybody in the next one. Later.